مساء الخير جميعا. Good afternoon everyone. On behalf of Princess Sumaya University for Technology, I would like to welcome Mr. Chuck Easttom. He's a fellow US scientist. He has a rather very impressive CV. He has 13 US patents, he authored more than 60 books. He published more than 40 conference and journal papers, and he has more than 40 industrial certification. Today he will be talking about applying graph theory in digital forensic investigation. So let's welcome Mr. Chuck. And
thank you very much. I will try to speak slowly because I have a tendency to get excited about the topic and speak too quickly. But I assure you, your English is better than my Arabic, so it should go well. I'm putting my website and my email up there. If later you would like to email me with a question, a comment, even a criticism, this is science and criticism is okay. If you see a flaw in the work, feel free. I did notice one of you is wearing an IEEE t-shirt. I'm glad to see that. I'm commenting on your t-shirt. I happen to also be on the IEEE Systems and Software Engineering Standards Committee, so I'm glad to see the IEEE. Although this is an ACM talk, I don't want them to get upset. This is sponsored by the distinguished speakers of the ACM, but I'm also with the IEEE, so I was glad to see them being represented as well. We're going to give you a basic overview of graph theory itself, very basic, and then get into how to model a forensic investigation with this technique. Now, 2 points I would like to make before we get started. The first being that this is not necessarily a brand new idea. I've already got 2 published peer-reviewed papers on this, and I've presented at many conferences and universities, but I keep expanding the work. And you are going to get one new thing that I actually was able to finally solve on the flight here. So it hasn't been published yet. I was working it out on the plane. What else do you do on a 14-hour plane ride except work on a new paper? But this also is important to me from a practitioner point of view. I also, in addition to research, actually work doing digital forensics for various companies, sometimes with police agencies, things of that nature. Last year I was in Lebanon training police officers there in digital forensics. And what I've discovered is we have a problem I believe graph theory can solve. The problem is this: when we have very complex digital forensics cases, such as network intrusion, trying to properly attribute the attack is very difficult. And police officers in particular aren't accustomed to this kind of crime. They're accustomed to crimes where the suspect you almost know before you start. So with a network intrusion, there are so many possible suspects. How do you identify one? In my country right now, everyone is blaming the Russians for every network intrusion. In fact, I'm told of people who have been arrested by the police for a computer crime, and the first thing they say is, "Oh, I didn't do it. The Russians hacked into my computer and they did it." Well, the Russians do have talented hackers, but they're not responsible for every hack in the world. That's just absurd. What I want to give you is a mathematical tool that can be used to completely model a forensic incident and then identify the threat actors with mathematical certainty. This technique began for 2 reasons. One, the complexity of these network intrusions that I already mentioned. Now, graph theory is not new. I'm very hopeful that some of you have taken at least discrete mathematics or a graph theory course and are familiar. If not, you know what you need to enroll in next semester. But besides that, Leonard Euler started graph theory in the 1700s. In the intervening years, it's been applied to, of course, network analysis. All the engineering students here have to have seen some graph theory with network analysis. It has even been applied to study the degeneration in neural diseases like Alzheimer's. But it was never before widely applied to digital forensics. Why? Very simply, most digital forensics people aren't mathematicians. And most mathematicians are not digital forensics people. I was one of the rare guys who's in both worlds. I also was speaking with some of the doctoral students before this, and I will advocate to you the same thing I did to them. The genesis of this idea and of many ideas comes from not being too narrowly focused. If you're only looking at one tiny, narrow area of academia, your answer could be over here in this area you're not looking at. This answer waited for someone who knew math and knew digital forensics. So I encourage you to broaden your horizons a bit. Now, graph theory basics are relatively simple. This is actually a diagram from a famous graph theory textbook. The idea looks simple, but let's look at what is happening. A graph, for those of you who don't know, is simply a pair of vertices and edges along with their incident functions. Now let's put that in a little better terms. Vertices are nodes that you're examining. In network analysis, they can be the routers and switches and various aspects of your network. The edges are what connect them. And the incident function is how they're connecting, what makes A connect to B. Fairly simple. As far as mathematics goes, basic graph theory is one of the easier things to master. It's not nearly as difficult to say differential equations or advanced matrix and linear algebra. So let's look at some essentials. A basic graph consists of these vertices connected. Now we're starting with no direction. A connects to B, we don't care how. If we have direction, then you put an arrow where it's going to, and we call that an arc instead of a vertex, and we call that a digraph or directed graph. Now, for pure mathematicians, they don't much care. For digital forensics, we will always deal with arcs. We will always deal with directed graphs because direction is really, really important. If I'm analyzing a network intrusion and vertex A is a person with their computer, and vertex B is a server, it is important which direction data flow. Did they upload something or did they download something? It's a very different story. So we have interest beyond the pure mathematics. And here's a basic diagram where we see directions of the arrows. Now this is something that most of the other types of modeling don't use. It's called a loop. It's when a vertex loops back on itself. Having applied this to real digital forensics investigations, that happens quite a lot. It's very common for some vertex, a server, to be communicating with itself. For example, Windows. If you're not aware of this, if you have Windows, any version, turn it on in an isolated environment, just you, at home on your home wireless network, and run a packet sniffer. You will see a great deal of traffic. Windows is talking to itself quite a lot, for various reasons. Now, a few things we need to be concerned with that are very important to us in our digital forensics. Degree of a vertex, that's simply how many edges connect to it, edges or arcs. And you can look at the out degree and the in degree, how many are coming in, how many are going out. Now, from a forensics point of view, that immediately becomes important. If I have more than one suspect in a network intrusion, and they both have a connection to the server that was broken into, which one has more of a connection? And this actually comes from an actual criminal case that was in the US approximately 4 years ago, and I was an expert in that case. A company had been breached. They accused an ex-employee of doing the breach. And yes, there was some network traffic from his home to their server. But there was also network traffic from multiple foreign IP addresses, including in North Korea, that they could not explain. Now, at that time, the notion of nation-state hackers like Chinese or Russian was not widely understood. And even the law enforcement officials investigating this thought that Chinese hackers seemed absurd, seemed like a spy novel, not reality. And ultimately they concluded that this individual had conducted the breach. But they never explained how, if it was him, what about all the traffic from North Korea? How did this man from his home route traffic through North Korea? I'm aware of proxy servers, but setting up a proxy server in North Korea is a non-trivial task. In any case, Using graph theory, we can see which one of the vertices have the most connections to our target. That's just a starting point. Adjacency, which vertices are connected by an edge. Now, it's very possible in a network intrusion that there's not a direct connection. I'm also very involved in penetration testing, teaching hacking techniques. And if I were going to hack into a target, I wouldn't do it directly from my computer. I would route through someone else. Anyone that has any skill does. In fact, in my opinion, if you trace the attack back to a direct source, either that person's not really behind it, or they're really incompetent. A real hacker would not do it that way. The directed graph we already discussed, and in our world, we will always use that. Now, weighting. This is an issue that I struggle with for some time, which we'll talk about momentarily. How do we weight the edges? One of the things I'm very unhappy with, and is related to this, is news reports where they talk about person A is connected to person B, a criminal, a terrorist, whatever. What does connected mean? Does it mean we once had coffee in the same coffee shop? Or does it mean we meet regularly every week? That's a very different thing. Well, the same thing is true here. You might have a breach to a server, and you can show that I connected to it. There is an arc going from me to that computer. But what was the nature of the connection? Did I visit the website one time? Or was I there constantly trying to log in unsuccessfully? Very different. So the weighting of these edges and arcs is going to be a very important part in threat attribution, understanding who did this. And we'll talk about methods to weight in just a moment. So we have a basic model here with all of our vertices and all of our arcs. Now the first thing in doing this practically, the first mistake you can make is not accounting for every vertex and every arc. Did you account for everything that could have connected to the target? For the rest of this presentation, we'll assume a breach of a web server. Do you have a vertex for every connection to that web server? If not, you're ignoring a possible source of the breach. Do you have an edge map or an arc map for every vertex that connects to that web server's vertex? If not, you could be missing a possible avenue of attack. So the step one, we create a model. Now this is a terribly simplified model. In a real network intrusion, the graph itself would be extremely crowded. The good news, for those of you who have not had graph theory, is, and this may sound odd, you don't necessarily have to represent the graph as a graph. You can have tables which simply show the incident and adjacency as number values that can easily be fed into a program to process. But in this case, we're keeping it simple. We've looked at 3 different suspects, and they each have an arc going to the target. Well, now we have to ask ourselves, which one has more weight? Now, momentarily, we'll talk about how to weight it. We have 2 different methods you can use. But after we've weighted it, at this point, with no further analysis, I would definitely consider suspect 1 before suspect 3. They have a much heavier weight. It seems much more likely they were behind the breach. Now, how do we weight the connections? This is the one thing I've changed while in flight here. First of all, weighting the connections is very important. You have to do it right, and you cannot allow your bias to come into it. Unfortunately, weighting can be based on a number of different things. How many times you connected to that server, the nature of your connection. Did you actually log in, or did you just visit a website? All sorts of things. So when I originally published this, I suggested instead a somewhat loose ordinal method of measurement, where you just have a few levels, such as level 1, casual and infrequent visits. You once in a while visited a website. 2, casual but frequent. Yes, you're just visiting the website, but you're there quite a lot. 3, some significant interaction. You've uploaded or downloaded something. You've done something with that server. You've interacted in a meaningful way. Or 4, you either had administrative access or you did some deliberate breach of the server. That would be the highest level of connection. Now, this ordinal method has been used in real cases, and it works just fine. A little later, we're going to expand that to a ratio method. But this was first proposed simply because it's easy to implement, and it doesn't have a lot of room for bias. If we have 4, maybe 5 different weights, not too much bias goes on there. So, with more complex views, you might have multiple points. For example, in this case, this suspect here has no direct connection to this vertex. But you can see they do have connections to 2 others that do have a connection. This goes back to our earlier statement that for this methodology to work, you have to make sure you map all the vertices. You didn't skip any of them. Now, the pictorial representation isn't even necessary. Here I've represented those same graphs as an adjacency matrix, just showing you which vertices are adjacent to each other, have a direct connection, and an incidence matrix. These are very often used, particularly with large, complex graphs, so that you can feed them into mathematical programs to analyze them and produce results. This isn't standard in graph theory, but for our purposes, I would recommend using an incidence matrix that includes weighting. Now, standard graph theory doesn't do that. We're kind of modifying the graph theory a little bit. So how does this help? First of all, before we go further, at this point right now, you have a way to lay out all the evidence in a case and look at it objectively. Now, I don't know how it works here, but unfortunately in the United States, we have a very bad problem with digital forensics. Oftentimes, the investigator is himself a police officer and not a separate scientific investigator. This is very different than, say, DNA forensics, where someone in a lab does the forensic analysis and just sends the report to the police officer. Well, when you're directly involved in an investigation, you're a human being, you're going to have biases. You might already have an idea of who you think is guilty, and you naturally want to shape the investigation towards them. Well, right now, we're going to add much more, but stopping right here, you can look at all the evidence in front of you in an objective fashion and step back from that bias. Also, I presented this about a year ago at the University of North Texas, and one of the attendees was an attorney, and he became very excited because he simply thought this makes a great visual aid at a trial. You can show the jury, look, here's the connecting points, and you can see it very easy, very visually. But we're going to add more to this. Now, weighting, we've already given you an ordinal method, and that can still be used. We can simply give these little levels of basically what the person did. But if you want to do a ratio weighting, it's very simple, and I'm embarrassed that this did not occur to me for the past 2 years of doing this work and publishing papers. I was actually in flight and reading a book on artificial intelligence, machine learning algorithms, and reading a section on different ways to do data normalization. And it just occurred to me, we can take any weighting you want and simply use the same data normalization we do in machine learning to wind up with values between 0 and 1. So for example, if you would like to consider the percentage of total visits to a site during a time of interest, you make that a percentage, you have a value between 0 and 1. Or the number of packets between 2 vertices during a time frame. Again, normalized, you'll have a value between 0 and 1. Total logins, now these are just 3 options, but you can literally use any metric you want, use standard normalization techniques that are found in even the most elementary machine learning textbooks, and you end up with a weight that's now a ratio measure as opposed to ordinal. Now, why is that probably better? First of all, ordinal measurements are given somewhat to bias. Who's to say what is strong connection versus a very strong connection? It's hard to say. But a number. This connection is weighted at 0.9, and that connection is weighted at 0.5. There's no bias there. If I use the same metrics for both weighting, the first connection obviously is much heavier, much stronger connection. An incidence matrix is just looking at the incidence between the various vertices, and here we see an example. This is also taken from a rather famous graph theory textbook. And we show it here in graph format. Now, evaluating the graphs. We can do our weighting, we can look at the vertices, we can use ordinal or ratio methods we've already discussed, but we can still add more. But if you stop right there with a weighted digraph using ratio weights, you already have a more powerful modeling tool than currently is used in digital forensics anywhere. And here's the weighted incidence matrix. Well, let's go a little deeper. What else can we do with graph theory? As a side note before we continue, when I first started doing this, I realized I didn't have enough graph theory knowledge, so I basically went to Amazon and bought all of the graph theory books. Fortunately, there's only about 15 or 16 books in existence on the topic, so it wasn't that expensive. Most of them are all introductory books that repeat the same thing. There's 4 or 5 that go into more advanced graph theory, so it's not too hard to find the really good ones. First of all, subgraphs. Now, mathematicians, again, are interested in this from a pure mathematical point of view, but I think if you're contemplating digital forensics, this would immediately jump out to you. It is very unlikely that 2 incidents, even if perpetrated by the same person, would produce an exactly identical graph. 2 different attacks on 2 different targets at different times. So I would be shocked if the graphs were identical. But it would be very interesting to me if there were significant subgraphs that were identical. Now, a subgraph is just any piece of that graph that you want to parse out. Now, from a pure mathematical point of view, even this H1 is a subgraph. But I think we would all agree this is not a very meaningful subgraph. You found 2 vertices and 1 edge that match. I could probably do that with any 2 graphs anywhere in the world. The more it matches, now, this is a much more meaningful match. This subgraph is a significant portion of the main graph. I see a lot of overlap. If I'm doing a forensic investigation and I'm looking at 2 different incidents and I'm trying to see if they were done by the same attacker, looking for large subgraphs is one method of doing that. Excuse me. For example, as I mentioned at the beginning, in my country, where everyone wants to blame the Russians for every hack there is, I strongly anticipate that if you were to grab a known Russian attack and then grab all the ones they're being accused of, very few would have a significant subgraph in common because it's simply media hype. There's no real reality to it. Now, this has been another area where we've gone a little beyond traditional graph theory. And I'll take a moment out to, as much as I love math, I'm going to criticize mathematics in general. And this term is a perfect illustration. I know many engineering and computer science students struggle most with their advanced mathematics classes, and I'm here to tell you it's not your fault. It's the mathematicians who want you to be confused. And here's an example. This word, isomorphism. It's a very complicated, scary sounding word. But what does it really mean? They're the same. It means same. Well, if they just said same, that would be easy to understand, but then the mathematics people wouldn't sound so smart. They like it when you don't understand what they're saying, because then they feel very smart. And I say that as a person who reads mathematics books for pleasure, but I must confess that we have a bad habit in mathematics of just trying to make people look stupid because we're using complicated words. Isomorphism, in pure graph theory, if 2 graphs have the same number of vertices, the same number of edges, and the vertices are all of the same degree, then the 2 graphs are said to be isomorphic. Now that's put in plain English. Just to illustrate my earlier point, this is the excerpt from Wolfram Math World. Much more difficult to understand, means the same thing. Now for forensic applications, obviously, if you had 2 truly isomorphic graphs, I would be shocked to begin with, but that clearly was the same threat actor. It would be almost impossible for someone else to have exactly modeled everything they did. However, This can also be applied to other areas. I'd like to say this was my idea, but the first time I was presenting this was a very large group at a conference, Secure World, it's a security conference, and there was a police officer in the group who came up later. And he said one of the problems he'd encountered was with serial killers. Once they've caught them, they have a tendency to confess to things they didn't do and to deny things they did do. They just, well, they're obviously mentally ill people. They would be serial killers, they're insane. He said using this to graph known crimes they had done and compare that to graphs we think they did, with all the different elements, what they call the signature of the crime, would be useful. So it goes beyond digital forensics, and I just wanted to put that in there, and I wanted to explain that that wasn't originally my idea. I wish it was. It was a police officer's idea. And here's a place I've stretched the math a little. And I'm waiting for some mathematician to give me a very difficult time over this. Pure graph theory doesn't really have the concept of a percentage of isomorphism. It's either isomorphic or it's not. Now they do have the idea that subgraphs are isomorphic. But I ask a simple question. If two different incidents that have been modeled with graph theory have a substantial, significant percentage of similarity, isn't that interesting forensically? It is to me. So I ask, how close are they? It's a very simple formula. I take the sum of all the vertices and edges in graph 1 that equal graph 2, and I divide it by the total number, and I end up with a percentage of isomorphism. In other words, if I can look at two graphs from two different incidents, and I can show that they are 98% isomorphic, well, that's pretty telling. That's indicative that we might have the same threat actor. And in incident response, this is becoming a huge deal. Let me divert for just a moment. I do research in a lot of areas, and one of the areas I've done a lot of publishing in lately has been cyber warfare. And no one wants to admit it, but every country engages in it. Every country has cyber warfare capabilities, and they do them. They just get very outraged when someone does it to them. And then they get on BBC News and say how horrible this is when they were doing the same thing this morning. But the problem is attributing who did it. If I have two graphs that are over 90% isomorphic, and I know graph 1 was from a specific nation-state actor, I'm much more likely to believe attack 2 was as well. But all too often, we make these attributions without any real knowledge, just based on gut level feeling. It just so happens in 2017, Saudi Arabia had a re-outbreak of Shamoon virus. And I happened to actually be on the Saudi Aramco compound when it happened, doing some consulting and training with their security people. What was odd is with no evidence whatsoever, everyone in the room started saying it was Iran. Just because they don't get along with Iran. You cannot get along with someone, that doesn't mean they're guilty of every crime that ever occurred. If we can map it and model it. Now I say again, partial isomorphism is not a factor of traditional graph theory. It's something I've added. This formula is something I created. Not terribly complicated math, but I just wanted to be clear on that. Another thing that we're interested in is the center of a graph. Again, mathematicians like to use fancy words that aren't necessary. Every graph theory book will tell you the center is the vertex with minimal eccentricity. Well, when I hear the word eccentricity, I think oddity. I have an eccentric uncle who behaves strangely. Eccentricity is defined as the distance between the vertex and the one farthest from it. In other words, the one that has the shortest path through the graph. That would have been a better way to say that than eccentricity, but again, mathematicians like to confuse you. Well, when I'm looking at a graph, a model of a forensic investigation, the center of that's going to be very interesting to me. It may not necessarily be the threat actor, but it certainly is something I need to examine closer. Now, I don't know how many of you have had real-world hands-on experience with investigating network intrusions, but they're incredibly complicated. And simply trying to identify who you think could have done this is a terribly difficult process. So a tool like this, if you at least start looking at the centers, that at least gives you a guide to begin examining who might have done it. Now, it should be noted that it's terribly common to have more than one center in a graph. It's not a big deal, it happens all the time. If the center is a device in a network intrusion, then these are the most important locations to seek evidence. Now, I am looking around this university. It's a large, impressive-looking university with a number of computer labs. I am guessing you have hundreds and hundreds of computers and probably a few hundred routers and switches. If you had an intrusion, what are you going to do? Go pull a log from every computer, every router, every switch on the campus? I can't imagine that's even possible. But if you can map out the intrusion and identify centers, now we go to the detailed analysis of those centers. We've now targeted a bunch of specific things to analyze. We've made an impossible task into something that's doable. Incidence functions. Now, even in pure graph theory, this never gets defined very mathematically. I know when I hear function, I'm expecting to see some sort of calculus type function up there. But in graph theory, we just are meaning what connects point A or vertex A to vertex B. So for our purposes, if it's a network intrusion, this will be a descriptive label. It will be nominal data. And for those of you who either haven't taken or don't recall your statistics, I keep referring to ordinal, nominal, ratio, the 4 types of measurements, from nominal up to ratio at the top with interval and a few others there in between. But we're using just nominal here. Visit the site, download the file, upload the file, and log in. Those are just options. Any other way you can describe what is the connection. Remember that in graph theory, incidence function simply means how is vertex A connected to vertex B. We know they're connected, but how? So for a network forensics example, these would be logical, descriptive labels for that incidence function. Now, a few concerns on weighting. Most people weight the edges, but graph theory allows you to weight the vertexes as well. Which one's most important? If I'm attacking a server, I'm probably going through a few routers. I'm not directly connected to the server. Well, those routers are vertexes too, but they're not that important. They were just in between me and the target. So they would get less weight. They're just pass-throughs. They don't matter. If you really want a thorough model of your investigation, I recommend weighting both. The edges and the vertices have a complete model. Now, in the United States, we have something called the Covert Challenge. You don't have that here because it's a U.S. federal law. But it's important. I just finished an article for Digital Forensics Magazine that's about to be published on using Covert standard as a framework for forensics everywhere. Let me explain what it means. If you wish to present scientific testimony in a U.S. federal court, the judge has to decide whether this is valid science or not. And unfortunately, the judge is not a scientist. How would he know? He was a lawyer. So there's a few things you ask about. One, has this scientific method been published in peer-reviewed sources? If it hasn't, it's very unlikely that a judge will allow it in the U.S. court. I have been involved in a few cases where the opposing side's expert was disallowed because he made up his own methodology, which may be wonderful and may be sound, but he hasn't published it anywhere. No one has examined it. Now, just a show of hands, particularly for the students, how many of you actually published a peer-reviewed article yet? I know several of you have. Got to be more than that. For those of you that haven't yet, let me tell you why peer review is so important. First of all, there's a very good chance of even a good article being rejected. You have 3 peer reviewers usually. They're going to do a blind review, and at least 2 of them have to accept it. They may not accept it for any number of reasons. You may get rejected and have to go to a different journal, or maybe make changes. There's a famous story of an economics paper that was rejected from 5 different prominent economics magazines. Now, why is that important? Because the author later received the Nobel Prize in economics for that same idea. In other words, just to get published, you had to pass through some peer reviewers, and I happen to be a reviewer for 3 different journals myself. Some reviewers are very studious and very careful. Others are just not. Some are just in a bad mood that day and reject you. It happens. Or you're publishing an article That's the opposite of their own publications in that field. Oh, they're going to reject you. They're not going to say yes to an article that renounces their own work. And unfortunately, the people reviewing are probably people working in the exact same field. That's why they were selected. So, the reason we say has it been published in a peer-reviewed journal is simply being published means you pass through some level of vetting, some level of verification. Second thing that happens, if you've ever been to one of the scientific conferences like IEEE or ACM, your paper will get published there, but you also give a presentation. Much shorter than these, they usually only give you 20 minutes, which is not enough time to give a complex topic. But what immediately happens after your presentation is question and answers. And not all the people there are very pleasant about it. Some of them want to pick apart your idea and attack it. So again, by the time you publish something in a peer-reviewed magazine, other experts have reviewed it and said this at least makes some sense. The other question asked in the Daubert standard in the US is, has this method been widely accepted in the scientific community? Now again, that's a US rule, but I think it's valid anywhere you want to present scientific evidence. You should ask yourself, is this good science? And two indicators are, has it been published in peer-reviewed journals? And has it gained wide acceptance in the scientific community? If you have a brand new idea, you may have an earth-shattering Nobel Prize-winning idea, or you may just be really, really wrong. And you'll never know until it's been reviewed. Well, what I put on this slide were the presentations for this day that you're seeing today. Each one in each publication has been added to and expanded, but these are the various presentations at major conferences, including one in Egypt about a year ago. And these are the various peer-reviewed papers. There is an expanded version that's just been submitted to an IEEE journal. We'll see what they say. Specifically applying this only to network indicators of compromise. And there's a more general that I just got word this weekend has been accepted for publication in a digital forensics magazine, and it's geared more towards practitioners. So we have 5 peer-reviewed papers already on this topic, another one pending. Not to mention, this is based on graph theory. Graph theory is not some new cutting-edge science that's unproven. It's 300 years old, and it's well proven. Areas for further research. Or put another way, why did I come halfway around the world to give this presentation? Aside from the fact that I was looking for good matzah and Arabic coffee, which is very hard to get in Texas, by the way. I live in Texas. They don't have matzah in Texas. Aside from that, I am hoping other people will take this and write their own papers. Even if those papers are critical, that's fine. Or maybe add to it. But areas I can see that need to be added to right now. We've already looked into degree of isomorphism. That can be expanded and made much more mathematically rigorous and more acceptable from a pure math point of view. That's an area that would render a paper. Other forensics disciplines. I mentioned a police officer mentioned to me serial killers. Well, DNA forensics, fingerprint analysis. I don't know if you're aware of this, but around the world even, there is not a set standard for what makes a matching fingerprint. Each lab makes up their own standard. How many points make a match? Well, graph theory would allow you to match all the points and create a model. Weighting methodologies. Well, I've gone from an ordinal to a ratio through normalization. That is new. I've just added that, so that certainly could be expanded upon. And just a case study, taking any case where you know the outcome, it's not in doubt, modeling it, seeing how close the model comes to the actual facts. These are 4 proposals, 4 areas that would warrant a research paper that anyone could write. If you do choose to write a paper and you'd like more data, please email me. I'm happy to give it to you. I'd love to see some papers on this topic. Frankly, like mentioned, I've written a bunch of books, which is true, but I always tell my wife, writing books doesn't mean you've done something important in science. People writing books about you means you did something important in science. Einstein didn't write any books, but his name's in every physics book. So having someone write a paper on a topic I've created would delight me to no end, and I'd be happy to help in any way I could. Conclusions. This is a tool for modeling forensic investigations, and it's ready for courtrooms. It has been subjected to peer review. It has been at many, many presentations, both scientific and industry presentations. and well received in every one. More research is needed, as I just pointed out. Now, I'm leaving this slide up that has my website and email, and I'm going to open the floor to questions or even just comments or criticisms. Feel free. Don't be shy. I'm not easily offended, even if it's a criticism.
Have you used this in any work cases?
Yes. I do a lot of work in digital forensics, and I actually volunteer my time with a group we have in the United States called the Internet Crimes Against Children Task Force. It includes federal and local law enforcement that investigates online crimes against children, and I've used this to model some of their investigations. And it was effective. Those were great case studies because normally the suspects in those cases end up confessing, because once they find the person and they look at their computer, there's such overwhelming evidence that they really don't want a jury to see, so they wind up confessing. And so it was very easy to verify that yes, the model matched the person who actually confessed.
The waiting process, the page rank page ranking algorithm that they use
Any type, once I've moved from ordinal to using normalization, page ranking algorithms could also be used as long as you normalize them. You're normalizing them here for the same reason you do in machine learning, because different sets of data have different ranges, and if you don't normalize them, they won't have any interacting meaning.
Yeah, one more thing about the similarity ratio. Are you looking for a specific method in the graph and trying to match it with that method?
Well, what I'm looking for here is just some indication that the two incidents can be traced back to the same person. So if I look at a percentage of isomorphism between the two graphs, there isn't an established threshold for how much says yes, it was the same threat actor, but it's enough to guide the investigation.
You can look at it as a key, try to match by key structure on the graph and try to find this.
Well, that's certainly a possibility. However, if you get too small, basically what you're talking about is small subgraphs.
Yeah.
If you get small enough, then the problem is I'm sure you'll find that match in many graphs, and it's not meaningful.
This is why I said what kind of method we have.
What I'm looking for is a percentage for the entire graph. I don't want just isolated subgraphs because I'm sure I'll find them and I'm sure they won't mean a lot. It's like identifying a burglar and you narrow it down, well, he picked a lock. Well, I'm sure many burglars picked a lock, doesn't mean it's the same burglar. Other questions or comments?
I believe that different cases very different weighting. So how we can come up with a weighting that can generalize over multiple cases. I believe also that in real cases we end up getting maybe 1,000 of those.
Yes.
So we have to come up with weighting methodology that could be optimized and generalized for multiple cases. This is one useful thing for this work also. We can think how we can mitigate after like can help us for forensic, and it can be helpful for mitigation. Once you said it's hard to get full identical graphs, but we can come up with subgraphs. Those subgraphs could be the path that the attacker usually, it's a weak path that could be allowed the attacker each time to reach the destination. So we can think also how we can mitigate after we forensic this or modeling this. So I think there's a lot of things to do for us, for our students.
I agree with everything you just said, beginning with, in a real network intrusion, 1,000 or more vertices would be, yes, I can see that. As far as the weighting, that's the area that needs the most additional work. So we've gone from an ordinal to a ratio that's normalized, that's an improvement, but yes, optimizing that so you can have the same weighting mechanism across multiple dimensions, That's an area of improvement of research. In my opinion, identifying additional areas of research is not a negative on any idea. That's actually a positive. A good science should fuel more research. If you publish an idea and no one ever cites it and adds to it, you probably have a bad idea. So I agree with you 100%. I would love to see someone take this and work better on optimization. I will eventually get around to it, but unfortunately, you have to wait until the idea comes to you. You can't force it. And someone else may actually be far better qualified than I am with optimization algorithms, and maybe even do a better job optimizing than I would. As much as I'd like to be, you can't be an expert in everything. Very good comments, I totally agree. Anyone else? Please.
Do you think we can look at it as like personalized intelligence? What I'm trying to say, because I'm trying to map it into what dynamics can do these days. They consider like person X, but we do in like certain circumstances. Do you think we can characterize the attack or whatever you call it? Sorry, I'm not from
That's okay.
So we can associate behavior with each attack.
If I understand you correctly, that's been suggested by other people at these presentations, particularly people from a psychology or criminology background. Can we use graph theory to basically graph to the attacker?
Yeah. This is what
I would think it's definitely possible. I don't have the strong background in human behavior to do that. Like most math people, human behavior is a mystery to me most of the time.
now I'm thinking, I'm looking at it as like the, what do you call it, decision system. That given like attack as a specific attribute, what kind of person would do such an attack?
It certainly is plausible to me,
Yeah.
and it's been suggested by criminologists to me, but I don't have the knowledge of human behavior to do that. But yes, it seems, as I said at the beginning, if you just do a Google Scholar search on graph theory applications, graph theory itself has already been applied to degenerative neurological diseases, to all kinds of things. Basically, it's probably one of the most versatile mathematical tools there is, and I'm very hard put to imagine something you couldn't do a graph on. Other questions or comments?
Any boundaries for using graph theory or
I'm sorry,
any boundaries or constraints that does not apply when using graph methodology?
none that I'm aware of. The only constraint would be is to make sure you're very thorough in putting in all the vertices and edges, and as was already mentioned, that's going to be a huge graph. But if you don't do that, then you're not really modeling the investigation. You're presupposing what's important. The idea of this is to model it and then let the graph tell you what's important. Now, once you've graphed and weighted it, you may look and say, 2/3 of my vertices are unimportant. They're continuous connection at best, and then you may focus on what's left, but you have to start with looking at all the vertices and all the edges, which, yes, is a daunting task. But right now, doing incident response for digital forensics is a very difficult task already. We're just trying to streamline it a bit. Anyone else? Well, go ahead.
I want to ask about weighting methodologies. I think that if an individual connecting to the target very much or frequently, this doesn't mean that he is under attack. I think that we have to study the normal behavior and the abnormal behavior. For example, studying the normal in degree or out degree or something like this, then decide that this is attacker or not. Also, the type of the attack is different in different cases. If we are detecting botnet or malware communication or denial of service. So I think after weighting the methodology, we have to propose a methodology to detect the attack. For different attacks, there is a different methodologies.
Well, you're exactly correct, and I hope I wasn't unclear earlier and misleading. It is not the case that simply because a vertex and an edge has a lot of weight that that's the person who did it. That's not what I'm saying. I'm saying that that means that's a vertex and an edge you need to look at closer. But for example, on a website that's been breached, I bet the website administrator has a very strong weighting to it. He accesses it all the time. That doesn't mean he attacked it. All I'm saying is that the weighting can help you narrow down, because as we said, you're going to have thousands of connections. Can we at least pick which ones are worth looking at? Not all of those are even likely suspects. Some are, if you were to have an attack on Amazon.com and weighted, you would find my wife weights very heavily on that. That doesn't mean she broke into Amazon, that means she shops online a lot. That's all it means. But it would mean looking at that, at least to figure out what is that about, and then maybe dismissing the person. There is no formula we can put in and say, boom, that's the person who did it. All we can do is help focus where we're going to look closer, but you're exactly right. Anyone else?
I want the Covert Channels. You can't always model this. These take into consideration these Covert Channels inside this network attacks.
Well, I'm so glad you asked that question. Before this talk, I was having a conversation with one of the PhD students about covert channels. Some of my earliest research was in distributed steganography and things of that nature. Obviously, if I can't detect the communication, I can't model it. So if it's truly hidden communication that I never detect, it won't come into my model. But frankly, in most network intrusions, at some point there's an overt communication aspect that can be modeled. Besides that, a model that shows a gap may at least indicate there could be a covert channel that I need to investigate. In other words, I'm seeing everything modeled here, and I still cannot account for data exfiltration, for example. That's a great use of covert channel. I've modeled everything, I've looked at all the heavily weighted vertices, and I can't find how the data was exfiltrated. That might lead me to look deeper and to contemplate covert channels. But no, I cannot model something I cannot see. That's just the fact of life, that we can't do that. Other questions or comments?
It's a constraint.
I guess that is a constraint. That would be a constraint, absolutely. Well, thank you for your time and attention, and great, very good questions.
تم حكم في قاعة 109 ومناقشة أفكار مشاريع تخرج والريسيرش